Rn is what we call a vector space. A vector space is a collection of objects called vectors that satisfy certain conditions to ensure that any linear combination of the vectors in Rn stays in Rn. It's still another vector. Vectors can't leave Rn by adding them or scaling them to each other. The reason I bring up vector space is because we are going to look at a very closely related idea. Sometimes different sets of vectors within Rn form their own little universe. So we say that subsets of Rn can form what are called subspaces. So a subspace, its definition is a set in Rn for which any linear combination of objects in the set is still an element of the set. Any linear combination of vectors in the set is still a new vector in the set. This has three consequences. This is a linear combination of this set of vectors. So this stuff right here is called the set. It lives in Rn, so it's called a subset of Rn. If I form a linear combination of them, I'm trying to see what I can create from this recipe. Any linear combination has to contain 0, because you can take the 0 weights for all of it. We say that it's closed under scaling. Anytime you scale a vector in the subspace, it stays in the subspace. And it's closed under addition. Anytime you add two vectors in the subspace, they stay in the subspace. Why do we care? Subspaces have their own important properties. They have geometric interpretations, which we're going to use later in the course. The most important thing is that they will give us some more insight into solution sets for two important systems, ax equals 0 and for ax equals b. And those solution sets we're going to talk about a little bit later. So just to try to give you some examples of what I'm saying by subspaces, so let's say that L is a line that's spanned by the vector u1 and 5 in the vector space R2. So in terms of a picture, I've got this vector and it kind of points up. When I say it's spanned by a line, that talks about any linear combination of this vector u. There's only one vector, so the only kinds of combinations that I can do are just multiples of it. I can add it to another version of itself, but it's just going to give me some vector that's a multiple of u back again. When I take all the different multiples, it just gives me some line L. Is this a subspace? Absolutely. I can check those conditions. Yes, it does contain 0, because if I take no bunches of u, I'll get a 0 vector again. It's closed under scaling. So if I take any multiple of u, it's in the line. It doesn't leave the line, and it's closed under addition. If I take some alpha u and I add it to some beta u, it's going to give me some multiple of u, and that's in the line again. So yes, this is a subspace. This line was created by a span. So the span of any set will always form a subspace. Just by definition of span, it's always going to satisfy those conditions. Is the set of points in and on the unit circle in R2 a subspace? And the answer here is going to turn out to be no. Why wouldn't this set be a subspace? So we are talking about every point in and on the unit circle. So I'm going to give you two examples here. So I'm going to take one point that lives right there at the 1, 0. And then I'll take another point here that lives at 0, 1. So if I call this one u and I call this one v, if I add the vectors u and v, I'll get 1, 1. But this point 1, 1 is not going to satisfy the equation of the circle, x squared plus y squared equals 1. The set is not closed under addition, and that means this specific linear combination is not in the set. And if it's not in the set, it can't be a subspace. Subspaces have to be able to allow infinitely many different linear combinations, but there has to be something special about them. If you extend this, you can talk about subspaces of R3, One of the subspaces of R3 could be the set that just contains the 0 vector, because obviously this set contains the 0 vector. Any multiple of the 0 vector is just the 0 vector, so it stays in the set. And adding any elements from the set, 0 plus 0 will still produce 0. So this is still in the set, so this is a subspace. You could talk about a line formed by the span of some single vector, a plane formed by the span of two independent vectors, and you could have R3 itself. If you stick within these little universes, any vector within them stays there. It can't ever leave. You can talk about a basis for a subspace in the same way that we talked about a basis for Rn, and a basis for a subspace, so let's call a subspace V. So let's say this is any set in V that spans V and is linearly independent. And then very closely connected to that, we're going to talk about the dimension of a subspace. And the dimension of a subspace V is the number of basis vectors for that subspace. So kind of going back to these definitions in what I talked about above, the dimension of a line is related to the number of independent vectors that you need to span the line. To span this line, you only need the one vector, and it's a non-zero vector, so the dimension here would be 1. So a line is what we call a one-dimensional object. If we have two independent vectors, they span the plane, they are independent, so there are two basis vectors here, and the dimension would be 2. A plane is a two-dimensional subspace. As we talked about, the dimension of R3 itself is 3. What would the dimension of this be? Any multiple of 0 will give you 0. So by definition, that's linearly dependent. So because there aren't any basis vectors, we will say that the dimension of this set is 0. So let's say I have V1, V2, and V3, and this is a set in R4. Each one of them has 4 entries. Now, if I say that H is just this set, this is a subset of R4, but it is not a subspace of R4. Because if I were to go V1 plus V2, that vector would not be in the set H. The first two components, 7 plus 4, would give me 11. I don't have any vectors with an 11 component. But if I say that P is the span of those 3 vectors, then this is a subspace of R4. Any span is always a subspace. Anytime you create something via span, it will always be a subspace. I would love to know what the dimension of this subspace is. Take these vectors, by definition, V1, V2, V3, span P. Are they linearly independent? You could take those 3 vectors, put them into a matrix, but just to save you a bit of time, I'm going to tell you that there is a non-trivial way to make these vectors add up to 0. So the set is linearly dependent. And that means it is not a basis for P. So I would like then to find a basis for P. Clearly, V1 and V2 are not multiples, and that means this set V1, V2 is linearly independent. Now note, if I take the span of any one of those 3 vectors from the ones I was originally given, it produces vectors that look like this. Some bunch of V1, some bunch of V2, some bunch of V3. But I know that there is this dependence relationship. I could, for example, take V3 and isolate it. Any vector that I would form in this way could be written as follows: minus 5V1 plus 3V2. And that means any generic vector X could then be C1 minus 5C3 bunches of V1 and C2 plus 3C3 bunches of V2. That's just some bunch of V1. That's just some bunch of V2. And so the point of the story is a generic vector from this set is equivalent to a generic vector that looks like this. The span of just those 2 vectors, V1 and V2, is the same as the span of all 3 of them because the 3 are linearly dependent on each other. I know that V1, V2 are linearly independent. I know that V1 and V2 span the plane P. and therefore v1, v2 are a basis for P, and because there are two basis vectors, the dimension of P is equal to 2. P is a plane in R4. It's a two-dimensional subspace of R4.